This stone right here is just about the most outrageous opal I've ever seen, or it's certainly one of them. It is completely outrageous. And it has honeycomb, which is a kind of cool stuff. It makes this pattern in the stone do like really cool things, like these. They they start in one part of the stone and then like fade off through the other part. Look at that! Isn't that cool? I mean, it is outrageous. And I threatened to dye it black. And I wouldn't. I never would have dyed this one black. Or even tried, even though we know that you can't dye it black. I don't want to ever hurt this thing, man. It is totally beautiful. Look at that, huh? Oh, wowie, man. I mean, wowie. And, you know, it's not black at all. There's nothing black about this stone. And it is one of the brightest stones I have ever seen, ever. In 30 years of cutting black opals almost exclusively, this is one of the brightest stones I've ever seen because it's not the body color that makes it bright, that makes it outrageous. It's the stacking order of the spheres. The spheres that make up silicon dioxide come from the particles of clay in kaolinite clay. Each particle is two layers, one of silicon dioxide, one of aluminum dioxide. During opalization, the aluminum oxide is stripped away. It leaves the silicon dioxide with a charge imbalance. It was joined to the aluminum oxide with a hydrogen bond. And that bond is that the energy of that bond, half of it is carried with the silicon dioxide, and it needs to bind with something. And during opalization, the presence of iron oxide or iron sulfide will precipitate the opal from the clay. It does so very rapidly in both light opal and dark opal. Light opal is by iron oxide. Iron sulfide makes black opal. And it does so quicker because it has more energy. The sulfur, the ferric ion donates two charges, two electrons. In the sulfide, in the iron sulfide, there is an extra electron that comes because of the size of the sulfur ion, I guess. I don't know. I have not been able to actually watch it. I just know that it happens. Okay, anyway, iron sulfide is not black in the molecular form. It is, however, absorbs light, and that's what makes black opal. But it's because of the energy that made it is stronger that black opal is usually brighter than light opal. But not always, is it? Not always. It's not the body color, it's the stacking order. each sphere is surrounded by 34 other spheres. 34 spheres touching each other with one in the center. All the way through this stone. Huh? Those things are a few nanometers, 200 to 350 nanometers in diameter, half the size of the wavelength of visible light. The more homogeneous the size, the brighter the stone. That's what the secret is. It doesn't matter what color the body is. It matters how well organized the opal is. And the more homogeneous the body, the size of the spheres is, the more organized this is. Because of simple geometry, not magic. It's a chemical reaction and the geometry of spheres. We can describe it all mathematically and reproduce it in the laboratory. Peace, y'all.